Okay, the rate of the number of bacteria Y in a culture is directly proportional to the number of bacteria present. Okay, so they're telling us that the rate of the number of bacteria in a culture, so that's going to be called Y. So that rate is dy dt. It's proportional to, so that means it's equal to K times something. And what it's proportional to is the number of bacteria. But the number of bacteria is represented by Y. So the rate is proportional to the number of bacteria. So I set up what we call this differential equation. And then here's some initial conditions. There are 2,000, so Y equals 2,000 when time was 0. So there's my first initial condition. And then my second initial here is when time is 3, Y is equal to 10,000. Okay, the first initial condition always helps you to find C, and the second initial condition helps you to find K. The question is, how many bacteria were present when T equals 5? So they're really telling me find an equation for Y as a function of T, and when I get that equation, plug in T equals 5 and tell me what Y is, and then you round your answer to the nearest whole number. All right, so we've got a differential equation, and remember that they don't tell us, but when they say if we need to find the number of bacteria, we need to solve for Y. So we want to move from dy dt to Y, and so we're going to have to integrate. So first you separate, okay, so this is a Y and this is a Y here. So I'm going to move all the Y's to the left, and I'm going to move all the T's to the right. So first you separate, then you what? Then you integrate, all right? So let's integrate this left side. So just to make it clear, this left side is really 1 over y dy, the integral of that. So this is ln of y plus c, but I'm going to move all my c's to the right side. And the integral of k dt is actually, k is just a constant, I could actually move that out. So that'll be k times the integral of dt, which is just t plus some c. All right, so first you separate, then you integrate. Sometimes you exponentiate. Do I need to exponentiate here? Well, I have to solve for y, and so if I e this, okay, on both sides, then what will happen is the y will fall out. All right, so this becomes y is equal to akt plus c. This c, I had to e both sides, so this whole kt plus c was a family, okay? And this is actually equal to kt times e to the c. I can go backwards on that and see if bases are the same. I add exponents. Okay, these are exactly the same thing. But e to the c is really just another constant because e is a constant and c is a constant. So what I do is I call this c a c1, and I make a new c called e. This new c is equal to e to the c1. And this would be c times e to the kt. All right, so first you separate, then you integrate. Sometimes you exponentiate, and then I solve for y or c. And here I solve for y first. I could certainly have solved for c in this blue equation here. You could try that at your own time. I actually think it might have been easier. But what I have here is y equals cekt. So I have two unknowns here, the c and the k, that are constants, and I can find both of them because I have two initial conditions here. So let me start with my first initial condition. My first initial condition says any time that time is 0, y is 2,000. So this is going to tell me, let me plug this in here, this is going to tell me 2,000 is equal to c k times 0, which is just 0. E to the 0 is 1, so c is equal to 2,000. So if I plug that c right here, I'll have y equals 2,000 ekt. All right, I'm almost done. I just need to solve for the k here. And so to solve for the k, I'm going to use this second initial condition. And this says anytime that t is 3, y is 10,000, so say 10,000 is equal to 2,000 e k3, so that's 3k. Divide, I need to get the e by itself to solve for this k. So just to make sure we understand, this really is the answer for y equals. I just can solve for the k, so I'm going to do that here in blue. So I'm going to divide both sides by 2,000, so that would give me, let me put it over here, 2,000. So that would give me 5 over here is equal to E3K. I need to get the K on the ground by itself. So what do I need to do to both sides? I need ln both sides. The left side is ln of 5. The right side, if you log a tree, the cat falls down. So K is equal to ln of 5 over 3. Make sure that you don't say ln of 5/3. That is not the same thing as ln of 5 over 3. Okay, this ln of 5. The ln only works with the 5. It's a function of the 5, not on the 3. Okay? All right, so then I plug this k in right here. This is going to give me y equals 2,000 e to the ln of 5 all over 3 times t. Okay? And then if I have a calculator, I could plug in t right here. And I do have a calculator. So this is how many bacteria were present when t is 5. So I'll plug in 5 right here, and I will get the answer. But let me just show you. If I didn't have a calculator, I can manipulate this a little bit more. This is really 2,000 e ln of 5 times t over 3. Okay, and then I can put parentheses right here, because a power to a power, you just multiply these powers together. Now, if I multiply these powers together, I do get the same power here. And so what I get is y is equal to 2,000 times, if you log a tree or tree a log, the cat falls out. So this 5 falls down. But this t over 3 does not fall down. So that's actually another way to write this problem. So the answer actually for the equation of y can be this, or this, or simplified a little bit more, this right here. All right, so if I wanted to know the answer to this first question, how many bacteria were present when t equals 5, then I would get my calculator out. And put in t as 5 right there. So that's going to be 5 raised to the 5 over 3. Remember, exponents before multiplication. So I need to actually do this part right here before I multiply. And so I'm going to plug in t equals 5. So 5 raised to 5/3 is that. And then I'm going to multiply this by 2,000. And so the answer is y equals 29,240 number of bacteria. All right? All right, please make sure that you can do this problem. And let's go back to this song here. The answer of how many roads must a man walk down before they call him a man? And at this time, you don't need to write this in your warm-up. I'd like to read what you have in your warm-up, but without my telling you my answer. Of course, this is an open-ended question, so there are many answers, but I don't know if you know this song by Bob Dylan. Okay, it actually has to do with calculus. I don't know if he knew calculus, but it is a calculus song, and it's going to help us to understand slope fields today. The song goes like this. How many roads must a man walk down before you call him a man? How many seas must a white dove sail before she sleeps in the sand? Yes, how many times must the cannonballs fly before they're forever banned? The answer, my friend, is blowing in the wind. The answer is blowing in the wind. And this right here, sorry I wasn't there in person to sing this for you. just my terrible voice on the mic will have to do. But this right here is the calculus part, and we're going to be graphing slope fields. And when we graph slope fields, the answer, and the answer to differential equations is always y equals something. You know, when you solve the differential equation, it's y. Okay, so y is going to be what we are graphing. It's going to be what's blowing in the wind. All right, keeping that in mind, let's go ahead and go to slope fields. So before this, before today, anytime I asked you to solve something, I gave you a differential equation that was separable, meaning you could separate the x's and y's, but not every differential equation is separable. And when it's not, we can draw a slope field for it to get the answer, or the y value. But we can still do it if it is separable. So I wanted to start with this problem right here. We're going to draw a slope field for dy dx equals 2x. Not only is this in your notes, it's also number 4 in your homework, so you could do it in either place. It's nice to do it twice. Maybe do it once in your notes with me today, and go home and see if you can do it on your homework. Or you can just do it straight in your homework. But let's look at how you draw a slope field. This one's separable, so we could do it both ways. But I want to logic this through with you first. If dy dx is equal to 2x, okay, so if this is true, and we are trying to find what y is equal to, okay, first you separate, so you have dy equals 2x dx, then you integrate. Okay, so what I'll get is y plus c, but I'll move my c to the right side, is equal to x squared plus c. And so this is what my solution will be. The solution to this differential equation is x squared plus c. And that means the c can be anything. So what that means is, let's say the c is 3. So y equals x squared plus 3. If I take the derivative of both sides, wouldn't that give me 2x? Yeah, so y equals x squared plus 3 is an answer. What about y equals x squared plus 1? Is that an answer? Well, if I take the derivative of both sides, I get 2x. So that's also an answer. So one answer to this differential equation is y equals x squared plus 3. Another answer is y equals x squared plus 2, x squared plus 1. Another answer is y equals x squared plus 0, right? Y equals x squared plus pi. Even y equals x squared minus 1, right? Let's see, y equals x squared minus 1. Or y equals x squared minus 1/2, right? As long as this is a plus c, and c could be negative, that is an answer. The derivative of this is going to be 2x. So there's an infinite number of answers for this differential equation. Now, when we give it an initial condition, this doesn't give an initial condition, but when you get an initial condition, then there's only one answer, okay? But this doesn't have an initial condition, so we're going to have many possible answers. All right, so how do you graph this? Well, to graph this, because there's just not one answer, we graph a whole bunch of all of these answers. So, you know, one possible answer is y equals x squared. So y equals x squared, you know, looks like this. It's not a very good picture. You know, something like this. Another answer is y equals x squared plus 1. So another answer looks like this. Another answer is y equals x squared plus 2. Or y equals x squared minus 1/2, right? Y equals x squared minus 1. So there's actually an infinite number of answers to this differential equation. And so to represent that, we can draw a slope field, okay? So what is a slope field? A slope field is just kind of like an electric field, okay? And it's a field where if you just blow in the wind, if you follow the wind, you will draw all the possible y's that you could have for the answer to that differential equation. So how we draw a slope field is we actually start with a little t-chart, okay? on the left side you have x, then you have y, then you have dy dx. All right, it's just like a t-chart when you have x's and y's, but now you have 3 columns, and you pick a point. So let me pick, let me draw the slope field over here. Okay, let me pick a point here, which is 0, 0. So if I pick 0, 0, what is the slope? The slope would be 2 times the x value here, which would be 0, which is 0. So any y that went through 0, 0 would have a slope of 0. So whatever y looked like, you know, when it went through here, it would have a slope of 0. So the slope, it should be a horizontal line, right, when it comes here. So it turns out right here, at 0, 0, the slope field would be a horizontal line. What about if I had the point 0, 1? So here's this point 0, 1. Okay, what would the slope be for this solution of dy dx equals 2x when x equals 0 and y equals 1? Well, you just plug it into this formula. That's 2 times 0, which would also be 0. So if I had a y, if I were drawing y and it had a slope of 0, what would it look like? It would be a horizontal line right there. And it turns out, you know, anytime x is 0, there's going to be a horizontal line here. So I can draw all of these. All right, if I had 0, negative 1, this would still be 0, this slope. All right, and then I just try other points, and this is how you draw your slope field. So let me try the point over here. This is 1, 0. So if I put 1, 0 here, I get 2 times 1, which is 2. So if y were being drawn through this point, the y would have a slope of 2. And what would a slope of 2 look like? Well, something like this, right? Up 2 over 1, okay? So then I just draw right there, something with the slope of 2. What about right here at 1, 1? What would the slope look like of y? Well, again, be 2 times the x value, which is 2. So that would also be a slope of 2 right here. So I'll just draw this here. What if I had, I don't know, 1, negative 2? So that's, let's see, 1, negative, that's this point right here. All right, what would the slope field be right here? Well, the slope would be 2 times 1, x value, which is 1, which is also 2. So it turns out that for, let me see, for every, yeah, these are just duplicates of each other. So for every x value of 1, you're always going to have a slope field of 2. What if my x value were negative 1? Then what would happen is my slope field would be negative 2, right? It'd be 2 times negative 1, 2 times negative 1, 2 times negative 1, which would be negative 2. So a negative 2 slope would look something like this, right? Okay, so something like this. So then that slope would be also the same here, and the same here, and the same here. And so these points would all have the same slope of negative 2, right? If I plug in negative 1, 0, which would be right here, negative 1, 1, which would be this point here, the slope would all be negative 2. What if I had a point over here? This point here is going to be 2, 0. All right, what would that slope look like right here of the y if I drew y in here? So 2, 0, I have 2, 1, this point 2, 1 right here. And I have this point 2, negative 2, so 2, negative 2 right here. What would the slope look like going through these points, the slope of y? So this would be 2 times 2, 2 times 2, 2 times 2. All of these would be 4. What would a slope of 4 look like? Pretty steep, right? Slope of 4 looks something like, I don't know, something pretty steep, something like that, right? And so, again, that gets duplicated everywhere where this is these are some big slope field lines, but everywhere where the x value is 2. Okay, what would happen if the x value were -2? Right? Then these values here would all be -4. So what would a slope of -4 look like? Something like that. Okay, so this would be duplicated here. And then finally, what if I went through the points over here, where this point here is 3, 0. This point here is 3, 1, right? Over 3, up 1. This point down here would be 3, -2. Let me change these to 3. What would the slope through those points be? This would be 2 times 3, 2 times 3, 2 times 3, actually be 6. So even a steeper slope, right? So something like this, all the way down. And then over here, if I put in -3, it'd actually be -6. So I'll just go ahead and draw something super steep. And it's probably a little bit steeper. Okay, all the way down. And so what happens is I get this slope field. Okay, so I'm going to pull out these points. But these slope fields all get put together to form the slope field, the solution for this dy dx equals 2x. And so what would happen is I'm given a point. So if I say, okay, well, what if the initial condition were, let's say, 2, 2? Okay, actually do something a little harder. 2, see, initial condition -2, -1. Okay, then what I do is I go to that point, -2, -1. I put a big dot on that point. Okay, and I'd say, okay, well now there's an infinite number of possible slopes, possible y's here, but this one would signify a certain y equals x squared plus c, where when you plug in y equals -1, okay, and x equals -2, and I guess that would be what c is. C is going to be equal to -5. So when you have y equals x squared minus 5, that would represent this graph right here. And how would I draw that? I would say, I actually wouldn't calculate this. This is just telling you that, I know what this equation is. But on this slope field, if I didn't know how to do this analytically, I would just blow in the wind. I would just sing this song and say, well, the y is the answer. So I'd say, the answer, my friend, is blowing in the wind. The answer is blowing in the wind. Okay, and that should look something like y equals x squared minus 5. I guess technically minus 5 is all the way down here somewhere. So if I said, okay, what if I didn't want this answer? I wanted some other answer. I wanted the answer where the initial condition were, let's say 3/2, 1. Where is that? So that would be 3/2 is 1.5, 1 up here. It'd be somewhere here. And so what graph, what y equals would correspond with this initial condition? So I would just sing. I would say, okay, look, I know this is the way the wind is blowing. So I act like it's just blow. I just act like this is a feather blowing in the wind. And where would this feather go? It'd have to go through this point, okay? But the answer, my friend, is blowing in the wind. The answer is blowing in the wind. And you just you're just like a feather blowing in the wind. And you can see all these answers are x squared plus something, plus some c. All right, so the red here is the slope field. The green is the y equals something. It's the answer when you blow in this wind of slope fields. Okay. All right, so today we're going to draw a whole bunch of slope fields. And so we're going to start with one that's not separable. Okay, so let's look at this problem right here. On the last problem, we could separate and see that the y equals x squared plus c. But here, there's no way to separate this. If you move the y to the left, remember you have to use real algebra, there's no way to move all the x is to the right, because if I used real algebra and I multiplied everything by dx, okay, I would get this. And so now I have this, you know, expression here with the y and dx. So if I move that to the right, because it has an x in it, now I've unfortunately also moved the y to the right. There's no way to separate this problem. It's a non-separable differential equation. All right, so I cannot actually analytically find a solution to it. But what I could do is make a slope field for it, and then graph the solution if I had an initial condition. No initial condition here, so I would just graph the slope field. And so what we're going to do is we're going to, if I were in class, I would do WikiSticks with you. It's kind of a fun thing, but I'm not in class, so I'm going to show you how to do this. So first you just find 2 points. I like to start with 0, 0. You don't have to start with 0, 0. And you add the points together. So 0 plus 0, that'd be x plus y, which is 0. So I know the slope here is 0, 0. Where else would the slope be 0? What two numbers would I add together that would make x plus y equals 0? If they were opposites, right? So if x were negative 2 and y were 2, or if x were negative 3 and y were 3, right? They would all add up to 0. This would be x plus y. And so let me go find those points. So negative 2, 2, right? Negative 1, 1. So all these points here, you know, negative 1, wait, did I do that right? Positive 1, this is positive 1, negative 1, right? That would give me, if I add the x and the y together, x plus y, let me see, 1, negative 1. So this would be x plus y. This would also give me a slope of 0. So these points here give me a slope of 0. Also, let's see, I think that's pretty much it. All those points would give me a slope of 0. I need to go find some other points, so let's go find, this is a little bit harder than the last one we did. Let's go find this point right here, the slope here at 1, is that 1, 0? No, this is 1, 0. So at 1, 0, this slope would be 1. At 2, 0, right, this slope would be 2. At 3, 0, the slope would be 3. So actually the slope gets steeper as I move across. So I can reflect that here. Here the slope would be 1, and then the slope would be 2, and then here the slope would be 3. And it just gets, you know, steeper as you move across. Let's see, where else, I guess, trying to think how I would do this. I could move over here and say negative 1, 0 is negative 1, negative 2, 0 is negative 2, you add them together, negative 3, 0 is negative 3. So same thought here. First, the slope would be like a 45-degree angle like this, but then it's a little bit steeper, but it's a negative 2, and then it's going to be really more steep, which would be negative 3, okay? This point right here, this would be, what point is this? This would be 0, 1, 0, 2, 0, 3. All right, so what if I put those points in? 0, 1, 0, 2, 0, 3, 1, 2, 3, right? So again, the points will be steeper going up. This slope here would be 1. This slope here would be 2. And then this slope here would be 3. 1, 2, 3. A lot steeper, right? And then same thing here. If I put in, what if I put in negative 0, negative 1, 0, negative 2, this point right here, and 0, negative 3, then my derivative, my dy dx, is going to be adding these numbers together, negative 1, negative 2, negative 3. So same thing here. I start with like a negative 1 slope, but then it gets steeper to like a negative 2 slope, and then it gets really steep to a negative 3 slope, okay? What if I went over here to 1, 1? So if I had 1, 1 here, my slope would be 2, right? Here my slope would be 2. So all the places where you would add up to 2, right? I actually don't know where else you would add up to 2. 1, 1, maybe 2, 0, 0, 2, 3, negative 1, and where else would you add up to? I guess those are the ones I'm seeing. These will all add up to 2. So all of these points would have a slope of 2. So 1, 1 would have a slope of 2. And really the slope of 2 is the same as, you know, let's see, if I were to get it right, it'd be the same as, you know, this slope right here, right? That was a slope of 2. So 1, 1 would have a slope of 2. 2, 0, which was right here, would have a slope of 2. 0, 2, where is 0, 2? 0, 2, I've already gotten that. And then 3, negative 1. So 3, negative 1. So this right here would also have a slope of 2, right? 3, negative 1. Okay. Let's see. What if I tried right here? This would be 1, 2. So 1, 2 would have a slope of 3, right? This right here would have a slope of 3. So I'll just put in a slope of 3. This one right here, this was a slope of 3 right here. And if I did 1, 3, I would actually have a slope of 4. So this right here is even steeper. To think about how steep it would be. Something a lot steeper. Trying to, if it had a 4 slope, it'd be pretty steep. So this is a 3 slope, so I'm going to make it a little bit steeper here. That's going to be a 4 slope. Let me just write here. Slope equals 4 here. Slope equals 3 right here. So I remember. Right here, this one would be 2 over 2. This would be 2, 1, right? 2, 1. So that slope would be 3. So that would be the same as this slope right here, right? So this slope also would be 3. This point right here is 3, 1. So this slope would be 4. If I put 3 here, 1 here, that'd be 4. So this slope right here was a 4 slope, so I'll move that there. This point right here is 2, 2, so that's also a 4 slope. So I'm going to make that a 4 slope right there. Okay. These slopes right here, I believe, will be 5 because this is a 3, 2, and this is a, oh, this is a 3, 2. This is a 2, 3. These slopes will be 5. Wow, 5 is an even steeper than a 4 slope, so let me just make it kind of like that. That's an even steeper. And then this right here is a 6 slope, so that's almost a straight line. I'll do that. Okay. This right here, I want to just make it a little bit steeper than the 4. So there's the 4, so I'll make it a little bit steeper than the 4. Probably not doing a good job. So that will be right here. So that's a slope of 5, and then that's a slope of 6. Down here, this is going to be 3, negative 1. So this is a slope of 2. Down here, if I had 3, negative 1, that would be a slope of 2. The slope of 2 is the same as this line right here. This right here would be 3, negative 3. No, 1, negative 3. Wait, this is 2. This point over here is 2, negative 1. 2, negative 1. That's a slope of 1. Okay, that's a slope of 1. So that's the same as slope as this right here. This point right here is 3, negative 1. This is a slope of 2 right here. This point right here is going to be 1, negative 2. 1, negative 2. So if I put 1 here and negative 2 here, that's a slope of negative 1, which is the same as this one right here. Okay, and you can see how to do this. I'm going to stop there. My next slide will show you all of the slopes done, and when they're all done, they look something like this. Okay, when they're all done. Okay, so I want you guys to look at your homework. We've already looked at number 3. I want to talk about number 7 through 10 and do 17 with you. All right, so let's look at number 7 through 10. You'll have this on your test. I think also on your quiz on Friday. But what you're going to do is you're going to match this equation, the differential equation, to the correct slope fields. There's several ways to do this. One is to look at the ones that are separable. So for example, this problem here is separable. If I separate this, I would get dy is equal to sine x dx. And then I integrate. Remember, first you separate, then you integrate. If I integrate this, I would get y is equal to the integral of sine x. So that would be negative cosine of x plus c. And remember, the answer would be blowing in the wind. So which one of these, so just think about it, like which one of these problems, if I graphed in here, if I graphed in here, which one would be this answer? Y equals negative, cosine. Oh, look at this one. Y equals negative cosine x plus c. Does that look like a y equals negative cosine x plus c? Yeah, so this one right here is going to be, number 7 is going to be c. And then number 8 is x minus y. This says I'm going to get a slope of 0 anytime x and y are the same, right? Anytime x minus x and y are the same values, I'm going to get a slope of 0. So if you look at my choices here, here's, the diagonal 1, 1, 2, 2, 3, 3, 4, 4 are the slopes 0. What about this one? 1, 1, 2, 2, 3, 3 are the slopes 0. What about this one? 1, 1, 2, 2, 3, 3. What do you know? Negative 1, negative 1. Are the slopes equal to 0 there? Yeah, they are, right? All these slopes were horizontal. So this answer right here is D. This one right here is also separable, right? Like this one was not separable, number 8. But number 10, I could separate it like that. First you separate, then you integrate. All right, so this would be y is equal to x squared over 2 plus c. So, I've already figured out D and C. Between A and B, which one looks like x squared plus c? Remember, y equals is the answer blowing in the wind. So if you blew an answer in the wind, which one would look like an x squared over 2? And that answer is B. Like these look like x squares, right? Okay, and so that leaves you with this answer here being your A. And you can check that. When y is equal to 2, you should get 0. So where is my y equal to 2? Well, y equals 1 is this row right here. Y equals 2 is this row right here. Are all my slopes 0 there? Yeah, and if y were equal to 1, all my slopes would be equal to 1. So here y equals 1, are all my slopes, do they look like a slope of 1 here? Yeah, they do. All right, so that's how one way to do it, the slope fields going backwards. It's definitely not as easy going backwards as it is going forwards. Let's look at number 17. Over here it says, on the axis provided, sketch a slope field for the given differential equation. So you're just going to plot some points and figure them out on this problem. I'll plot some of them for you, but you can certainly finish up what I don't do. So if I put in x equals, let's see here. If I put in x equals 0 and y equals 0 at this point, I do know I get 0, 0. I also know if I put in any x equals 0, I'll get 0. So so anytime x is 0, all these points are where x is 0, right? Because this is 0, 2, 0, 1. I get horizontal lines. But I also know every time y is equal to 0, I'll get a slope of 0, right? So what I have is horizontal lines here also, okay? Sometimes if your denominator is y, like here, if my denominator y could not be equal to 0. So then what happens is you just have a whole bunch of points where you don't put any slope field because there's no y possibly going through that point at all. Okay, so if you have y equals 0, if y were on the bottom, you would have no slope field on y equals 0. You just wouldn't put any dash there. Okay, and then if I said, let's see, if I said x equals 1 and y equals 1, then the slope is 1. If I said x equals, that's what I'm doing. If I said x equals 1 and y equals 2, the slope would be, oops, that's not right. If x equals 1 and y equals 1, the slope would actually be 1/2. Right, 1 times 1 over 2. So that's up 1 over 2. Up 1 over 2. So the slope would be kind of flat, like that. If the slope were -1, -1, okay, that's also a 1/2 slope. So I'm going to go over here, -1 over -1, and I'm going to copy this slope right here, right there. If I had -1, -1, +1, I'd have -1/2, and if I had +1, -1, I'd have -1/2. So that's this point right here, I believe. This point right here is -1, +1, so the slope would be -1/2. So it's going to be something like that, and that slope right here is going to be copied right down here. This point right here, 1, 2, right here, if I put in 1, 2, I'll actually get 1, and if I put in 2, 1, I'll also get 1, because this is equal to x, y over 2. So I'm going to plot a slope field of 1 right here, and that's also the same as if I had 2, 1. So that's the same as this point down here. It's also if I had -1, -2, right, or -2, -1, right, those would also be, oops, a slope of 1. So -1, -2, ooh, I don't have that point, but -2, -1, I actually do have that point. So -2, -2, -1, which is this point down here. So I'm going to copy the slope of 1 right there, okay, and this point right up here would be 2, 2, I believe. So if I put in 2, 2, I would get a slope of 2. So to do a slope of 2, that would be like a little bit steeper. I don't know if it's that steep, but you see something like that. Okay, and if I had over here 1, 2, this would be 1. This point right here would be 1, 2. That slope actually, did I do that right? That slope actually, that's actually not 1, 2. That's -1, 2. Okay, that slope would be -1 if I plug it into this equation here. So -1 looks like this. Also 2 -1 would be give me -1, right? So 2 -1 is this point right here. So let's see, that's this right here. So that could be copied down here. I don't know how far I need to take this. Over here, 1, 2, 3, 3, 1 would give me about 1.5 slope. So steeper than this one, but not as steep as this. I guess this is 2. I don't even remember the slope anymore. 1, 2, 1, 2. This was a 2, 2. So that slope here is 2. So somewhere between these two slopes. So maybe something like that. And then this point right here is actually 3, 2. So this slope right here would be a slope of 3, and that would be steeper than this one. So I think something like that. Something more steep. Kind of not that easy to do. Okay. So anyway, you guys can do the rest of the slopes. But that's the kind of the picture that I'm looking at. The first problem says, let f be the function that satisfies the given differential equation. So that's just saying the solution y equals is if you solve this analytically. Write an equation for the tangent line. Oops, it says write an equation for the tangent line. That just means point slope, okay, when they tell me that. To the curve y equals f of x, so that tells me this point is a y and this slope is a y prime through the point 1, 1. So I already know the point, and that's going to be the slope at 1, 1. And I need a number for all of these. So the question is, do I have an x and a y value? I do. Do I have a slope? Well, remember this is dy dx. That's what y prime is at 1, 1. I already know dy dx, right? So at 1, 1, that's 1 times 1 over 2. So that's actually a slope of 1/2. So what I get is the equation of a tangent line is y minus y is equal to the slope times x minus x. And that is the answer to the equation of the tangent line. And it says use your tangent line equation. So they're saying use this equation here to estimate the value of y when x is 1.2, right? So y is equal to what when x is 1.2? So you can put in your answer like this. And if you didn't have a calculator, we would know y is equal to 1/2 times 1.2 minus 1 is 0.2 plus 1. And so this is my answer. You could actually just leave it just like this. But, well, actually, I don't really need a calculator. 0.2 divided by 2, isn't that just 0.1 plus 1? So this answer is 1.1. All right, let's look at letter C. Letter C says, find the particular solution to the differential equation with the initial condition. Use your solution to find f1 of 2. So this is saying, don't use the tangent line to estimate the solution. Actually, really find the particular solution. These phrases, when it says solve for y, find the particular solution, you know, find the equation of the curve. I think there's different ways to say this. This all just means find y equals, okay? Do this problem analytically. So first, you separate, okay? Don't move this 2 over to the left side. You want to move only things that you have to move to the left side, because eventually you need to solve for y. You need to clear the left side for just y, okay? If you move that 2 over, it just makes things a little bit more difficult for you. You just have to move it back. So first you separate, okay? Then you integrate. So first, oops, I didn't mean to do that. So first you separate, then you integrate. So when I integrate dy over y, remember that's really this, okay? I'll get ln of y plus c, but I'm going to move all the c's to the right side. Then you integrate this side, so this is going to be 1/2 times x squared over 2 plus c. So what I get is ln of y is equal to x squared over 4 plus c. So first you separate, then you integrate. Sometimes you exponentiate. Do I need to exponentiate here? Yes, I do. Okay, so I'm going to exponentiate. When I exponentiate, I get y equals to e. I exponentiate this whole side, okay? So the 4 x squared over 4 plus c must all go up in the air, okay? So that is what my y is equal to. The only thing is, this is really ex squared over 4 times e to the c. Remember that. And because of that, this is really just some other c. So I'm going to call these all c1s, and I'm going to call this c, some other c. So this is going to be c times e to the x squared over 4, okay? And this is my answer, except that if I have an initial condition, I am able to find c. So the question is, do I have an initial condition? I do. This right here says anytime x is 1, y is 1. So what I do is I plug that in to find the value for c. And so what I get is c is equal to 1 over e to the 1/4. And don't let all these fractions bother you. C can certainly equal that. So what I get down here is y is equal to 1 over e to the 1/4 times e to the x squared over 4. And that is my value, my equation for y. Now, this is kind of ugly, so I can simplify that, okay? This is really the same as y equals e to the x squared over 4 divided by e to the 1 over 4. And since the bases are the same, I can subtract the exponents, right? So what I get is y is equal to e to the x squared over 4 minus 1/4. And that's, I feel like, pretty much as simple as I would like to make it. All right, so there's my y equals. Then it says use my solution, and this is my solution, because when you solve a differential equation, you get a y equals. Find, if you plug in x equals 1.2, tell me what your y is. So what I do is I plug in 1.2 for my x, and I find my y. And so here I really do feel like I need a calculator. So let me pull up the calculator. This will be 1.2 squared divided by 4, right, minus 1 divided by 4, or minus 0.25, and that's 0.11. So what I get here is y is equal to e raised to the 0.11. So let me do that. Second e raised to the 0.11. And so that answer is y is equal to 1.116. Remember, you always have to go 3 decimal places, or and round correctly or truncate. All right, and that's my answer for f of 1.2. All right, oops, didn't mean to do that. Let's look at letter D. I think this is letter D somewhere here. Compare your estimate of 1.2 in part B to the actual value of 1.2 in part C. What's your estimate? Is an overestimate or underestimate? Okay, so if I go, this was analytically, I got 1.116. Using a tangent line, I got 1.1. Okay, so what it's saying is I don't know what the curve is. Okay, so I don't know what the curve is. So I have some curve. Okay. And it's saying go to 0.11. So go to this 0.111, okay? Estimate, get a tangent line there. Okay, so I got a tangent line. Estimate what the real value at 1.2 is. So here's the real value at 1.2. How close am I using a tangent line versus the real value? This is using a tangent line. So this is an estimate, using estimate of y using a tangent line. Okay, so reading off this green graph, coming over at, at 1.1. At 1.1, reading off of this green graph. Sorry, no. But then I plugged in 1.2. Okay, so this, at using this green line at 1.2, what y value did I get? I got 1.1. But the real value, okay, so this was actually solving the real value. If I graph this, what was the value of y when I plugged in? And so it turns out that the actual value is bigger than the, so I got the actual value, 1.116 is bigger than the estimate. So this, remember, is the approximation. That's part A. Part B gave me the actual, okay, and the actual is bigger than the approximation. Okay, so I would say the approximation is an underestimate. All right, so then let's look at this question. The question is, was your estimate an underestimate or an overestimate. So remember, the estimate was 1.1, and that was less than 1.116. So I would say the estimate was an underestimate. Okay, use your slope field to explain why. Okay, remember, when we're using tangent line approximations, okay, if your second derivative, so y double prime at 1.2, is positive, okay, then you have what's called an underestimate. Okay, if your second derivative at 1.2 is negative, then all your tangent line approximations, guess what? They're going to be above the actual value. Okay, here all your tangent lines will be below the actual value. And so if we go look at our slope, okay, so go look at our slope. Okay, this is already drawn in. But if we go to 1.2, so 1.2 is somewhere right here, and come up, oh, this is really the plot right here, at 1.2, and blow in the wind, sing the song. The answer, my friend, is blowing in the wind. The answer is blowing in the wind. Then, do you see you get something concave up? And if you see you get something concave up, then any tangent line you draw to it is going to be below the answer. And so therefore, the answer is an underestimate. Okay, so explain why. I would not say this. Okay, I would say the second derivative 1.2 is greater than 0. You could even say, you know, concave up. Therefore, this is concave up. So my answer is, my estimate is an underestimate. And that's good enough to explain why. All right. Okay. I think you guys are armed and dangerous. Go for your homework.